Okay.
Yeah, on live, I think we are getting the feed. Okay, so will everybody will start at 11:05.
ಅವರೊಂದು 1 hour 45 to 1 hour ಆಗುತ್ತೆ. ಅವ್ರು ಮಾತಾಡೋ ಕ್ವಶನ್ಸ್ ಕೇಳ್ತಾರೆ, ಐ ವಿಲ್ ರಿಪ್ಲೈ ಟು ದೆಮ್.
100 ಬ್ಯಾಟರಿ ಏನಾದ್ರು ಆಗಿದೆ ನೋಡಿ, ಅದಿಲ್ಲ ಇದಾ ಯಾವ ವಿಷಯ ಇದಾ ಇನ್ನೂ ಚೂರು ಮುಂದೆ ಬಂದ್ರೆ ಹಿಂದೆ ಚೆನ್ನಾಗಿತ್ತಾ?
ಪರ್ಟಿಕ್ಯುಲರ್ ಯಾವ ಜಾಸ್ತಿ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡೋದು ಅದ್ರ ಮೇಲೆ ಜಾಸ್ತಿ ಫೋಕಸ್
ಇದು ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡ್ತೀನಿ, ಆಮೇಲೆ ಇದಕ್ಕೆ ಇಲ್ಲಿಗೆ ಏನ್ ಮಾಡ್ತೀರಾ, ಇಲ್ಲಿಗೆ ಫೋಕಸ್ ಮಾಡ್ಬೇಕಾರೆ ಆಮೇಲೆ ಇದು ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡ್ಬೇಕಾದ್ರೆ ಇದರಿಂದಾನೆ ಮಾಡ್ಬೋದಲ್ಲ. ಎದ್ ನಿಂತ್ಕೊಂಡು ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡೋದು ನೀವು. ಅಲ್ಲ ಇದು ಕಾಣಿಸುತ್ತಾ, ಇದನ್ನ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡ್ಬೇಕಾದ್ರೆ ಇದ್ರಲ್ಲಿ ಮಾಡ್ಬೋದು, ಈ ಕ್ಯಾಮ್ರಾ
Okay, I think we should start. So here we have Venkat sir. Everybody knows him. He's going to steer this session. So I hand over to you, Venkat sir.
ಮಾತಾಡ್ತೀರಾ?
Hello, everyone. So we are delighted today to welcome Professor M Chandrasekhar from IISc live, coming to you live from IISc Bangalore. And it is a delightful experience for all of us because we get to hear him. We'll also get to see what all he's doing. He's one of the foremost pioneers in photonic quantum computing. Okay. And today we're going to learn what he's building. You know, he built India's first 6-qubit quantum computer, photonic quantum computer. And you're going to hear about it from him. You're going to see it and understand what is going on. Okay, so this is a very, very special live session coming to you live. Okay, so, but before we start, you know, just to set the context and to understand the mind of Professor M Chandrasekhar, sir, I want to ask you, why photons? What makes light such a powerful and attractive platform for building quantum computers? I know you've built the 6-qubit quantum computer, photonic quantum computer, the first in India. It has come out of your lab. It has been in the news. But tell us, why photons?
Yeah, thanks, Dr. Venkat. So, photons are two reasons. One, I personally like light a lot because that's the way the world is enlightened, right? So, second, I mean, to be more technical, light does not interact with the environment, and that's one of the key aspects for me to choose photon for building qubits and quantum computer. There are other aspects of it, which is that everything you need to build the system can be done at room temperature. So that will allow us to manipulate and control light in a very efficient way, or engineer them as the way we want to control them and detect in a more easier ways. So that's one of the reasons. Of course, there are drawbacks. Probably I will talk about it when I explain about the systems. So like each system, there are a lot of positive things and drawbacks. For me, the positive thing right now is ease of availability of photons, and then the way we can engineer them at room temperature.
So another question, you know, building on this. So you built the 6-qubit quantum computer, the photonic one. Now, just take us 2 minutes into it, you know, just tell us what was the hard part in this? You know, why is this so special? What was so hard in this?
Okay, so as I said, photon does not interact with the environment. They also don't interact with themselves. So that's what it makes that, you know, it's robust against noise, but it's difficult to make gate operations between them. So the way people are trying to overcome this problem is, okay, we can make two photons interact and it can be probabilistic. So your gate efficiency, like, you know, when you're doing operations, we are successful with certain probability and many times we fail. But that was still considered as a good way forward because, as I said, photons are available in large number. Once you have a large number, you are okay to lose with a lot of them. You still get some results. So the hardness was making it deterministic. So we, in our 6-qubit, it's not just we build a 6-qubit system. We wanted to address this problem along with it. So we tried to take different degrees of freedom and then make them interact within itself. You know, photon is interacting with itself with different degrees of freedom. I'll also try to explain it in more detail when I'm, you know, making a presentation of the system. But that makes our 6-qubit very unique. So our 6-qubit system is a completely deterministic. We don't have to have a probabilistic nature that the success rate is with so and so. So its success rate is 100%. And then in terms of gate operations, so that's the uniqueness of our system. We only used 2 photons, and then we used 4 degrees of freedom of, like 2 degrees of freedom of each photon to make it 6 qubits. So in that way, it was 2 entangled photon, and other 4 qubits were part degrees of freedom, and we made a complete 6-qubit system out of it. So we could demonstrate all the gate operations quite efficiently.
That's exciting. Just hearing you, I can see the passion that is driving you. Now, I know you want to take this from lab to reality, right? So what are the biggest challenges in moving these photonic qubit systems into scalable machines? Because I think that's your next goal, right? You want to
Oh.
take this lab prototype, make it a real system which people can use. It is scalable. Where do you go from here?
Okay, so when we show the setup here, you'll see that these are all like made of bulk optics. So when we try to make them a compact integrated system, there can be some alignment issue with the light because lights have to pass through and then interact. Or there is optical components in which we need to make them overlap at a nanometer or like micrometer precision. So that disturbances are the one which is very a big obstacle for us at this level to take it out of lab. But still, I know in the background you would see a small 2-qubit machine, which is a prototype. It works efficiently. It depends on kind of usages you are looking at. So we are trying to address them by miniaturizing them to a good extent, and then have an optimization of the optical setup to some extent. But ultimately, after right now it's only 6-qubit. Everything is in bulk optics.
Did we lose, sir?
Yeah, I think some connection issue might be.
Issue.
So you're back. Yeah.
Oh, you're back? Okay, so sorry. So I would just try to, okay, I don't know where it got disconnected, but I'll try to, go over it again. So when we are trying to look at miniaturizations, there are few issues. Alignments are the something because we are using bulk optics. When I take the tour of the lab, you'll see. But we still manage to have a 2-qubit integrated device, a portable device. You can look at the background, and it has some practical applications. So when we start trying to build larger number of optical components, alignments will be the most obvious one, which will be the big roadblock. But the way to overcome is to go to photon integrated circuits, where one can build with waveguides and make them go through around, follow certain path, and then it can be detected. So that's one of the major hurdles which is there. The other one is, again, we said at the 6-qubit level, our scheme is deterministic. But if I want to scale it beyond that, it might again, I need to involve more and more photons. So then it can become probabilistic, but better than the other schemes. So we have to manage between the probabilistic and deterministic behavior. That's one of the other challenge which we are trying to address with our work, in the coming months to years.
So, Dr. Chandrasekhar, in this program, there are 50,000 students enrolled, so what's your message to these students? If someone wants to start their journey in photonic quantum computing, what are those skills they need to start picking up today? How can they, one day join you in your lab and help you in building these systems, have their own startups, all of those, how does this journey begin?
Okay, so quantum is relatively new for a large set of students, right? So in that sense, but optics is known to everybody. So we all been using mirrors and light is there. So a good understanding of optics is the first step, I would say. If you are very good at optics, if you can understand light well, how you can focus them, how you can. So if you understand them at the visible level, because all the light we see are visible, and I know how I can focus it, how I can defocus it, or how I can collimate it. These things are done, then it becomes easier to deal with even photons, which are invisible because they are very low energy, we don't see, but we can start imagining them, and you can control them just by measuring. And so I would say optics is the first important thing which they have to learn. I mean, make it very strong for them, and after that would be some basics of quantum mechanics so that you can put them together. Then that's quantum optics. The moment you are good with quantum mechanics and some amount of optics, then you can completely dwell into the field and then look at it. Even if you're not from optics or quantum mechanics background, for students, I would say that there is a lot of other electronic support system which would be needed to build, and then probably sensors, detectors need some sensors. And there are various other subtopics, peripheral, like what we call as a support systems for quantum. There are a lot of openings, and one can start building things, learning, and look at. So.
Okay, sir. And so to put together this program, AP government, Qkrishi, Qubitech, Wiser, they've all worked in tandem to make this happen today. So I'm now going to hand it over to Rishikesh to ask you some Gen Z questions. He's from the Gen
Yeah.
Z, they are your target audience here today. So Rishi, very quickly, please ask sir some of your Gen Z questions which you were telling me about, so that he's able to connect with this audience here today. So thank you. Over
Yeah,
to
I think, yeah, just moment, Rishi. What I would also say is that because you all have put in a lot of effort, this is the first time I'm also taking my lab live. So we
Mhm.
usually give lectures. So I said there are so many students, and for students, it makes a big difference to show lab. So it's also a great opportunity for us to reach out to students and open up the lab to them.
yeah. So yeah, thank you, Venkat sir, for handing over to me. And I would ask you, Professor, some general questions that a lot of my friends also keep me asking. Like they are also inspired from you and your your lab and everything, your work, and they have been following to you. So one question I'll start first from my side, and then I'll gather a few questions. So what is the most unexpected skill that help you succeed? Something student wouldn't guess. Like student won't guess that this skill is something that professor would have helped a lot to achieve what you have done today.
This is a very you can't pick one, so it's always a very difficult. But I will say one thing very interesting is that I am a theoretician by training, right? So I did a lot of theory. It's only pen and paper. When this scheme, which we have built in our lab, when I spoke to some experimentalist, in a way, say that this should be experimentally realizable, right? To make it deterministic and everything. And there was not a very strong feel for it. I said, my small drive, like taking a bold decisions that experimental, let me take the risk and then do, and that's something which I could make it work. So I see taking a big risk where you might fail significantly, or if you succeed, you would succeed reasonably. I think that probably is a very uh, yeah, I think that's one of my skill, I would say, because it's not easy to move from theory to experiments. What I also felt, I said, what would happen at the worst? I would fail, and I'll go back and again deal with my pen and paper and still start writing equations, right? So I am for edge next generation. I think that was what I would say, because the science has evolved significantly, that we don't have to say that I only do theory or I only do experiments, at least particularly in quantum, because experiments and theory go in parallel, and we are trying to look at building technology. And if you can complement each other, and if you have both the expertise, then that's the best thing for you to do.
Yeah, that's really a nice answer and good advice. So there is one question from one of my friend. So, sir, photons are very fragile and sensitive. In your experience, what's harder to control, photons in the labs or undergraduate doing experiments?
I mean, yeah, photons in lab is easier if you understand the math, right? So when I look at every optical setup here, everything is a matrix operations for us, because the way the light enters, they all follow the law which nature has defined for them, right? So, but then students do have a bigger uncertainty, which is beyond our control. So.
Yeah, it seems like
No,
okay.
I mean, it's nothing in the negative side. It's good for us, right? So dealing with a bigger uncertainty, that's how you make them sharp, but then you make them more and more sharper with time.
Yeah. So, sir, typically, like you are a night owl student or a early morning person, doing all the work in early morning, or you like you start the work and stay there until you finish, like whether it is night or something like that. So,
Yeah,
as a
I think
student,
so. So as a student, it was always like that. I know you have some problem, then you can't sleep, and you just have to work through it, and you won't get a sleep if you're trying to, some
mm,
codes are not working, or you're trying to do something in the lab. You just try to finish it. And right now, even my students do that. We do, because if they're on certain stage, we decide, okay, even if it's 10, 11, let's get some food here, have continue, finish it, because there's a drive and we want to see something, so that if that result has come, you can go home and sleep peacefully. Or else, even if you're sleeping, you are off into your bed. That's, the day or night, it's very, it's not defined. Your work defines you.
Yeah, so like yeah, work, like I think most of us now in our generation are also like that. So we are habitual. Basically, you raise early, start your work at 5. It's like we have been told like Brahma Muhurta and all the stuff.
Yeah.
But now like the things are getting changing even for the students, right? So everybody is like trying to finish their work and dedicatedly and everything.
And some of us as professors, we also try to adopt to students because we also have to learn a lot from them, right? Like when Dr. Venkat mentioned about Gen Zs, there's so many things to learn from them. So we also adopt sometimes to their timing and what they need and learn so that the work gets, collectively move forward.
Yeah. And sir, did you ever feel, panicking before your exams and every time? So as you know, you have been so in the premier institute, like for your masters and PhD. So every time, like, did you panic, or it was like now generally you have studied and okay, I'll go there and everything is, very easy for.
No, so I think one, no, I never panicked. But one thing which because there are a lot of students here, I should say, is that I didn't do my undergraduate in any IITs or anything. I was from one of the colleges in Bangalore, National College. But at that point, when I was trying to go to apply for a scholarship to Oxford or something, so I could have felt, oh, there are so many big institute students, there are a lot of graduate students from IITs. Should I compete with them? Will I be able to get it? No, so there's nothing wrong in taking chance. If you're good, you will get it. But of course, you need to, keep working hard. And once you are there, then you realize everybody are, it's ultimately it's the hard work and the number of hours you put in to learn and understand would make a big difference. So I never felt, that I had gone to that panic stage. But what I always felt which helped me is that at every stage, we have to develop some skill with whatever opportunity we get. And that makes us unique. Right? You would meet somebody, you attend some other seminar, and then you go and meet some other person, you learn something. And that is that combination which makes you unique in your learning process. And you need to know that. And that is your, game winning points. It's not that it's Oxford or MIT or wherever I was in perimeter. It's not just that alone. A lot of people go to Oxford, a lot of people go to Caltech, a lot of people go to MIT. What defines a person is the unique paths they choose. It need not be all this big Ivy Leagues, but it can be a combination of many things. And that's what students have to look into to make themselves unique to the rest of the others.
Yeah. I have last 2 questions from my side. So as a student, there like today there are smartphones, at your time maybe TVs and all. So as a student, so what were your distractions and how do you overcome them? Because now in today's like there is social media, Instagram, and like students struggle to get over this distraction and focus on study. So like at that time, how did you cope up with your distractions at those moments?
I don't know. I mean, compared to current generation, I think we had very less distractions. When I was doing my undergraduate in like early 2000s time, right? So it was only, I still vaguely remember it might be some, some sports, like it can be a cricket or something coming during exams time or a few things like that. Or school games, you're part of school games. But okay, I don't call them all as distraction, what we went through, because I was in scouting and something else, right? I was involved there completely. And that has also helped me to take challenges in life, right? Even today, research challenges, because that's where current generation, when we say people are using a lot of artificial intelligence, or they might be glued to YouTube or whatever, I don't know if that is what is called as distraction, but how they effectively make use of it for their learning and how they convert it for their career growth is the most important thing. And that's what one has to, reorient themselves. So I don't think that at least I've had certain distractions to comment significantly or to say how I overcome that. Now I have my students. For example, let me say there are so many students here who are doing my research in my research group. Of course, they do have their own different few things, like following some cricket very, very severely and probably something else. But I think it's okay if they have a balance, and I do see most of them do have a balance, and that does refresh them when they come back to lab and look at it. And I do make sure that they are, when we interact with them, that they are not extremely off track of what they are looking at. So
Yeah. And sir, like one more thing. So basically, you said, you didn't do your bachelor's from any IIT or some that level kind of college. So there are a lot of students joining us today who are from not from IIT, not from IISc or such top tier one college, but they want to do like pursue follow your footsteps, like pursue their masters and PhD at top institutes and all. So at that time, like what did you do something differently, and did you like were you unsure about your future, like will I get into this, okay, what will be will I get a job, or like most of the students from our age are in that phase, okay, so this quantum is also new for a lot of us, and so like is this how we are going to get excel in this field, if you are starting it at
so
today.
So I think, see, when we are trying to look at the time frame, like our generation or the current generations, or I've focused, not just me, I think I had some of my friends also. For us, the focus is that you have to keep learning, because that is the unique asset. And then you have to keep trying. It's not just, just try one place, you may not get it. So what, even now, when I look at interviews or when I try to select students, it's not that where you are coming. It might have a small point. Of course, you are coming. It kind of assures you that you already have a good training. But there is also trajectory. So if you are coming from a very, probably somebody is coming from a rural background with some vernacular learning, and they may not have a good. But at some point, when they are finishing their undergraduate level, and when we talk to them, we can see some small trajectory, and that trajectory helps us to project where they can go, right? So that trajectory is what is required. Learning trajectory which students display. They may not have a good communication skills, but if they could communicate that they have learned something on their own or with some help, which is beyond what is a regular curriculum, and that's what actually defines anybody to get an opportunity, even if you're not from IITs or Ivy Leagues, and that's what will take them there. I think even today, that's what we do when we are interviewing hundreds of students. Is there something unique from them? Along with it can be there are many times people coming from the best of the institute would decide that I worked so hard, why should I work now, right? And they do burnout, and they will not be suitable for research because they might want to quickly get to something and look at it. So a long passionate interest is by students makes a big difference here.
Yeah. So thank you. Like a lot of students were asked, has put up some questions to us, and you answered to them, not only mine but others, and that's great. And I think after your lecture, we'll have some Q&A from the audiences. Okay. And thank you for answering this question, sir. Yeah.
Yeah, and thank you, Dr. Chandrasekhar. It's been very exciting, and now we'll hand it over to you. Please give us your presentation, take us through your lab. We're all very excited to listen to you. Thank you so much. So yes.
Yeah, thank you very much. So I thought I'll give a quick overview of the field. So my screen is shared so that they can see.
Yeah. I think your PPT is visible, sir. So
okay.
You can.
Okay. So I just wanted to give, because there are a lot of students, and when we talk about how science evolved, nothing happens overnight. So there is a lot of work which goes behind to develop a technology. The whole idea of quantum began in 1900. So you can see in the slide that first 80 years was only towards developing theory and understanding that why is the world behaving like this? What is happening at atomic level? Is there some mathematics which help us to understand? So people spend a lot of time on that. There were debates, there were mistakes, there were corrections. It was nothing happens with the first go in a right way, right? So after all that, around 1980s, people could start doing some experiments to understand that. Just to say, okay, yes, quantum mechanics is right, the way it is trying to help us understand nature correctly, because there are some observations and it's only quantum mechanics which is helping them to understand that. So later, only in around 2010 onwards, we started having a very good control. There was few experimental demonstration. After that, we started having a very good control of atoms, photons, and everything. And that has led towards developing technology. We are currently at a very, very early stage. So we might say IBM is building something, Google is building something. So we might have something in our lab and China might be building something. But what we are all doing is we are trying to put things together and explore what quantum can offer to the world or what devices we can build. So it's after next probably other 10 years or 20 years, we will have a much more clear picture of what all are the most useful devices. It can be computing, sensing, or communication, which are coming out from quantum physics as a resource. So the field, or what we call the ground, is open for the next generation students to explore and then take this field forward. So that's what I wanted to show in this slide. So you all are like at the right time to begin exploring this area. So I still want to give what is so strange or unique feature of quantum mechanics. It's the way nature behaves, right? Everything we see, either they are particles or waves. I see waters, there are waves, there are sound, these are waves. If I have a stone, there are particles. If there's a bullet, there are particles. So we have so many things. But what quantum mechanics says us is the moment we start going down, make it smaller, or start seeing things at a smaller scale, it can be an atom or photon or an electron, then all these things have both the behaviors together. They are both particle and wave. It's just the way we see. If I'm trying to observe the wave nature, I can get a wave nature. If I want to just follow the particle behavior, I can get a particle behavior. If I'm not looking at it, I get to see both wave and particle behavior together. And that's what it's been explained in this slide. If I just have if I just have some photon, send like a particle, you are just have two slits open, you're just only one slit open. When one slit is open, you see them coming at one stage, one point in the screen, like one strip, right? The moment I have two, then what I should get is actually two strip, but what we end up getting is completely a wave. It means that the photon, which is following the two slits, are coming out and then interfering and forming a wave pattern. So that can happen only if they are wave, right? It's just like a water, but what I am sending is photon, and that's what was confused people, right? How can you have both wave and particle nature? Then they started, okay, but that's what we are observing. If you are observing something, then all that we are left is interpret and understand why it's happening like this. And we can't question, and I can't change what has been observed, right? So what we get is when we track the photon, the way it is going, whether it's going to slit 1 or slit 2, it just gives me a particle nature. When we don't observe whether it's going to slit, it goes like a wave, right? It's kind of very difficult concept to understand, but that's what led physicists to debate for 2 decades, 3 decades to see whether it was correct or not. But for years, experiments are proven and we take it. And I will give another example, a simple example, which is a beam splitter. Like, right now you all have seen mirrors, light goes through, it reflects. There is some part of light which actually don't get reflected. It just gets lost, observed. But I can build a very fine beam splitters. I'll show that in the experiment is set up later on, where you send a light, it can take both the paths. It can go straight or it can get split, right? If you see here, we call it as beam splitters. It splits the light into 2 parts, right? So now in this beam splitters, also explains us, can tell us whether photon can split or can it be wave or something, right? I have a small experimental description here. If there is a photon, if I have a beam splitter, then what would happen is photon has to split. If it splits, which means that it has to go at both the point or it has to get detected at one point. So if it's a particle which can't break, then it only goes and sits at one detector. If there are many photons, then half of the photon will go there and half of the photon will go here. If it's only one photon, then only one photon will be detected at one of the detector. So this, you can see here that your light goes through. If there's a beam splitter, 50% of them can go to detector 1 and 50 can go to detector 2. So now this demonstrates that a photon, there is another way we check this. If there is a detectors, right? Detectors, we can say simultaneously whether they detect or not, which means that at any given time, there is a single click on detector 1, or there is a simultaneous click at detector 1 and 2. So you will never get a simultaneous detection. So either you will get detector 1 or a detector 2, which means that photons don't split. So they are like particle, it only goes to one of the detectors. So this experiment actually confirmed that photons, don't split. And people have tried to see a next version. Okay, I split, and then again I have one more, beam splitter. You can see a photon goes through first beam splitter. There's another mirror, two mirrors in the path, and again you make them come at one point. You make them interfere just to test what happens. So surprisingly, what happens is, if it was a particle-like behavior, if the photon will go take one of the paths or another path, and you will end up getting 50-50 detection at both of the detectors, but that's not what happens when you try to do a real experiment. Just what it says, like photon takes path, it has to go to D1, or if photon taking one of the path, it has to go to D2. But the moment I'm having two beam splitters at 1 and beam splitter 2, you will end up getting all the photons going to only one detector and not as what we expected classically. So if it's a particle, it should just have 50-50 at both the points, but you will end up. And so what is happening here is interference. Though it's not splitting, it is still taking two paths and then coming and interfering. So that's what we call as a wave behavior. It's coming in. In a double slit experiment, which I showed in the beginning, a single photon is actually taking both the paths and then coming and interfering. It's the same thing is happening here. If I'm not measuring, if I'm not looking at it, it's like a wave. It is going on both the paths. It's again interfering at the second beam splitter, and that is causing a destructive interference, and you are seeing a detection at only one path. I can actually get a detection at the other one completely, and then no detection at the detector D2. So these two experiments confirms that there is a both wave and particle nature. Depending on how we are observing, we'll end up getting, right? So this is what we kind of say as a summary, is that knowing which path the photon takes, we can say that its particle behavior is observed. If I'm not knowing which path the photon is taking, then we can get a wave nature which is being observed. So this, if no information exists, so the way we try to look at this, because I have to go for computing and other things, and we can understand this from an information language. If there is no information of which path the photon is going, then it behaves like a wave. If we are trying to track if there is an information, then it behaves like a particle, right? So this kind of says that the photon has both wave and particle nature, and that's how we define many things in quantum mechanics. So that gives a big picture of it. Now, to build quantum computers, we need to use these things as a resource. So I just give another simple example. There is a photon. Now photon is entering, there was this experimental setup, and then I'm measuring something. I don't know what is happening inside, right? Just like something like this here. So this is, you can assume that, you have a beam splitter like this, right? I have a setup like this. Something is happening for the photon, and now I need to build a model. For example, I can try to see that there's one particular path it takes. I can call them as 0. And there is another one where I can call it as 1. There are two possibilities. Now beam splitter has to do something, right? I can write a simple math for the beam splitter. Mathematics would be that beam splitter will send photon with 50% chances, or with what we call a superposition, simultaneously along both the paths. So that is defined by this expression. So you might have done matrices in your +2, or even now in your college you will be doing, but that defines what happens to the light, right? When this is an operation which defines what happens to photons which enters there. So if I want to say now, just write those mathematics, for this each optical component, where you have beam splitter. The first state, when the light enters, it splits, which says it is simultaneously going into both the paths. And then if I'm doing it again, second time, there's a beam splitter, right? Again, there is an interference and I'm seeing an output at only one particular point. You can see there's a beginning. It began with 1, 0, and the final output is 0i. So now that is what is telling that you are having an interference, construct interference, and you detect at only one point. If I had 1, 1 or 1i or something, then I would have got 50-50 chances of being detected both the points. So what we or scientists did at early 1900s was try to understand, build such kind of formalism. So because what we are measuring is the final output, what we are sending they knew both of them. What I'm sending they knew, what they're measuring they could figure out. But what was happening in between, because you can't track the photons, you can't see them efficiently or effectively. So this math explained the dynamics which is happening, and this is a building block for us to build or to start building a quantum computer. Now when I say what is quantum computers basic element, it is qubit. Might be you all have already got some exposure to that. It's just not 0 and 1 like we do in classical computer. It can be 0 and 1 simultaneously together. That's what I said here. You have a light which goes from a beam splitter. It can simultaneously be at both the points. It can come out at both the points only when you measure either it's at 1 or 2. And now that possibility of coming simultaneously to both is helping you. If you see the image figure at the right, you see I can at every point I can keep one beam splitter, which means the same light now is in superposition of multiple paths, which is a unique feature which quantum mechanics is giving us as a resource. So that superposition is an elementary building block, or what you call elementary resource for quantum computers. And there is interference, right? The moment you have a wave behavior there is an interference. The moment you are making a measurement, then there's a collapse, there's a particle behavior. So both of them are there coming as well. So there is a simple mathematical representation for this, which is there in this slide. Slide where you can see 0 and 1, where now I can connect it whether photon is going straight from the beam splitter or getting reflected and taking another path. That will be my state and 0 and 1. So I can define my qubit as 0 and 1 depending on which path the photon is taking. Right? So that's how we define. So just like in an atom, you can define qubit in a similar way where you have a nucleus and an atom with the ground and excited state. Whether the electron is in ground state, I will call it a state 0. If the electron is in excited state, I call it a state 1. And if they can oscillate between them, then I can create a superposition of electrons in an orbits, and that makes an atomic qubit. So you can build an atomic qubit like that. And photonic qubit by using beam splitter. There is also polarization. I will also explain that as a possibility, right? So now I can bring them together. I can bring two photons, and I can make an Hilbert space, which is something like this, 0, 0, 0, 1 possibilities. So I can build multiple qubits, And the other resource which photons also, or any quantum system give us, is entanglement, right? So now because the superposition, which says you can have one particle at two places simultaneously. Now if I have a two particle and if they are in superposition, you can have a unique configuration like this. If it is 0, 0 and 1, 1, which means if first photon is in state 0, the second one also will be in state 0. If first photon is state 1, the second one also will be in state 1. Now, if I make them move away, tens of kilometers, then still I can instantaneously say which state these two photons are. And that is entanglement. That is, and again, a very useful resource which you have got from quantum physics or from nature to use as a resource to build our quantum systems. So as I defined, there are three important things, which is superposition, interference, and entanglement. And this is the key things which we use to do anything in quantum mechanics, right? Or to build quantum technology, and even for building quantum computers. So if I have 3 qubits or 3 photons or anything, then I can have these possibilities of having them superposition, this one possible state. Then I can, if I have large number of qubits, I can have them all in superposition, which does not happen with classical computers, which means that I can have, this is a resource for us. It includes all of them. It includes superposition, it can have interference in that, and it can also have entanglement. So that's the way we describe a complete composite system, right? So in general, what happens with because of the superposition or anything is that it gives me more option, which means the 2 to the power of n possibilities of representing. If I have just 10 qubits, I would have 2 to the power of 10 possible states I can generate, which means that I can have so many number of configurations simultaneously. And that is a big resource. If I have a classical system, I can't get such kind of power, right? So that's what it's trying to say here, right? But measurement might collapse at only one point. So I'll quickly give a simple overview of operations before I take to the experimental setup. So when you do talk about computation, what we do, even today I have a classical computer, right? I want to write 2 plus 2, or I want to say, please multiply some numbers for me. You are giving that numbers, the computer is convert them into binary, and it is changing that state, and it gives you an answer in binary itself. Your final answer is a string of binary, which is reconverted back to your numerical values, what I want. Even my alphabets are all converted to binary, right? So which means to do a computation using a quantum bits, then I need to change their states, right, or the operation, so that my final output will be different inputs than different than the output, and that will going to be my answer. So for that, there is an example here. What are the kind of operations I need to do? We do bit flip, we do an Hadamard operation, which means that taking them into superposition, flipping the state from one to other, and then what Hadamard operation does is superposition, as I've shown in the slide. So you have a combination of such kind of changes. You have identity, do nothing. You change flip, you change the bit from 0 to 1, or you change the phases, or you introduce some small phase angle, what we call phase gate. So these are the few set of operations which we need to build. So with this combination of this, if we can efficiently do the work, then our computers will be very efficient. So there's two. If I want to make 2 qubits interact, we call them as a control NOT gate. So it means that depending on my first, change the second one. Then I can make the second one as a first, right? Depending on my second, change the first state. So that will try to make these 2 qubits interact. So it means the moment I can make 2 qubit interact, I can make second and third interact, third and fourth interact, or first and fourth interact. So which means that then I have a complete control, even if it's 50 or 100 qubits. So they define this as a universal set of gate. If somebody claims that I have built a quantum computer, or I can build a quantum computer, then they need to first convince that I can demonstrate this set of gates in our system, right? Qubits we have. And that's something which I've tried to take. The other important aspect which comes in quantum system is the measurement, where when I said it's a wave behavior, but the moment I am observing it, it becomes particle and it collapses. So this is general measurement here. Superposition will be there during the process. When we measure, it collapses. General measurement. So it means that I can take a large number of systems and make a measurement on the subsystem and then get a different output. This is a small example here where there is a 2-qubit system. I can make measurement only 1 qubit and collapse there. But then if you see here, if I make a measurement, I will get 2 output. Only on the first qubit, I'll get 2 possibilities. With 50% probability, I get 0, 0, and 0, 1. With other 50% probability, I will only get 1, 0. So there will be 2 possibilities. So this measurement gives us certain outputs, and I can make measurement only on the subsets of it. So that's something which also people have efficiently demonstrated with various systems we have. So how does a classical bit differs from a quantum bit? So you can see, the measurement completely, can be done in a classical system. States don't change the measurement. They can be copied or they can be erased in classical systems. But in quantum system, they are slightly different. Your measurement, you can't make a complete measurement. It only gives you some partial information. State collapses. States also gets altered when we make a measurement, and you can't copy and you can't erase the information in the quantum systems. So sometimes it may, depending on the way you're looking at, so you can't copy. So isn't it a negative thing? But it's also a good thing that it's secure, right? If you can't copy, nobody can copy your information. So everything can be seen from both the perspective, right? If the states are altered during measurement, then aren't we destroying the information could be one of the questions. But you can make repeated measurements, and then you can get back the states which you think has been altered, and you can reconstruct and understand the system, whatever. So for every problem, there is some solutions which has been figured out to make the efficient use of the resource which we get from quantum system, like superposition, interference, and everything. Right. So there is a set of criteria which was defined long back by DiVincenzo to say what qualifies, because I'm talking about photonic system. It's superconducting system, ions or cold atoms, everything has to satisfy all these conditions, which you say they should be defined, well-defined qubits. You should be able to change their state, and they should remain quantum mechanical, because the moment you're disturbing or some environment affects them, they will not remain quantum mechanical. That we call as a coherence time. So they should take long time to decoher, becomes noisy qubit. You should be able to implement universal set of gate, and you should be able to make measurement. Like with photons, all these things are efficiently possible. I can define qubits very well using multiple schemes. I can initialize state. Photons don't interact with the environment because they are very robust against noise. There are various reasons for that, and that's something which makes it better than other system. And using combinations of beams. In the beginning, I introduced beam splitters, wave plates. I will also show in the setup here, will help you to control light. But there are advantages of photonic systems, that you can do things at room temperature. You can access multiple degrees of freedom, which actually I have not yet touched upon. When you say photons, we all might have heard about polarization, right? Horizontal, vertical polarization. I can change the polarization of photon very efficiently. I can take photons in superposition of two paths, and that is also another qubit. So I can control photons in multiple degrees of freedom. I can have photons in different frequencies, right? We all have different frequencies. We all know the light is composed of, white light is composed of combinations of lights of different wavelengths. So we have whole VM spectrum, and I can have photons in different frequencies, and I can actually even have them in superposition of two different frequencies. That also can make my qubit. So I can have a qubit of photons by using different degrees of freedom. That's one of the biggest resources which we get from photonic system compared to any other system. And most of the hardwares are like available easily, like beam splitters, wave plates, lasers to generate photons. Designing gate operations is one of the hardest part, because as I said, photons don't interact with the environment, they don't interact with themselves. That is an hard part. If they don't interact with themselves, then how am I going to make 2-qubit gate operations? So that's what was one of the challenges, and people have tried to address it in different ways, and we also have tried to address it in some different ways. So, and photons move very fast. Because they move very fast, it's not easy to control them. I mean, I can't make it go slow. I need to do all my operations by the time it reaches another end. But people have figured out ways to do that. And that's something which the challenge has been addressed effectively, right? So there are different ways, different schemes to do photonic computing. I'm not going to go deep into them all, because as I said, we are in the beginning of the quantum era, I should say, the technological era, where people are exploring all possible ways. Which one becomes most viable would be not the most beautiful and most difficult one. It would be the simplest, where people can build it with a lower cost and make it robust and usable, right? So to figure out which of this scheme is most efficient, which is people are exploring different ways. Like there are multiple ways here, which people are building photonic computers. What we are trying to look at is the first scheme, where discrete variable in using different degrees of freedom, but there are other approaches. And there's also special purpose quantum computers, which people have built already using what we call as boson sampling, where you don't do gate operation, but you can still do some kind of computation. So I will quickly, these are just an images to say how qubits are built using different schemes. In a discrete variable, I can take polarization H and V as a qubit. In a continuous variable, what we call, these are like wave packets. It's just like a waves. You can squeeze the light in one particular directions and another directions, and you can treat them itself as qubits. So you don't have to go with single photons. You can even still take a very shape control, because you are all still in undergraduate. I'm not going into deep quantum optics of squeeze states and other things, but you can actually make them change in their shape and treat different shapes as qubits. It might be slightly difficult, but people have mastered it, and then people have been using that also a resource for qubit. So these are just an example of how you can do gate operations by making photon go through different paths and these images, right? So I will showing the way beam splitter works here. Light enters, it can take different paths, and that defines our qubit. When I mentioned that photons don't interact, there is one specific example here. You can see at the bottom, if I'm sending 2 photons through a beam splitter, what we usually think is that, oh, 2 photons can take simultaneously both the paths, or 1 photon can go in one path and other photon can go in another path. But nature does not allow that. That's all, because you might have heard of bosons and fermions, right? Fermi particles and bosonic systems. So bosons have a unique characteristic. They always try to go together. The moment it meets another boson, they say, no, come, we have 2 bosons, we'll go together. They will not let them go separately. So the moment 2 photons enter a beam splitter, they end up always going simultaneously together. They don't go separately. That restricts in doing gate operations. People have tried to figure out ways to overcome that and do a 2-qubit gate operation. So this is a slide which explains that. I'll skip that to show how the setups looks like here. So there is an example, and I will also show that in the experimental setup where we can explain them all. So there is a bigger picture. Once you understand them all in the bulk optics, like using waveplates, beam splitter together, people have gone to silicon chips where you draw lines for photons to pass, make them interact, come out, and that will be like a small photonic chip which will do the computation task for you, right? So I will. These are some examples, but now I will try to. This is the picture, but now since we are already in the lab, I'll take you to a small tour of systems where we can show how photons are generated, right? And then the 2 and 6 qubits of thing. So just a very quick, I'll skip them. There's 2 ways. One, what we call as a down conversion process, which means that laser lights emits millions of photons, but that millions of photons together won't help us to have a single photon. There's some unique ways where we pass them through a crystal, and what crystal does is that there's some interactions which happens. It's just like an atom going to an high energy level. When it is coming back, it sees a metastable state, and then it emits 1 photon. When it comes to second stage, it emits a second photon. So 1 photon gets converted into 2 photons, but that happens 1 in a million. So which means that most of the photons just passes through without changing any of its behavior. But 1 in a million becomes 2 photons, and those 2 photons come in rarity, and that is what we use as extract a single photon. But they are probabilistic, the source, but that's still a very good source. There's another way which people do is that we call as quantum dots, where you can trigger a material, and that material, the moment you trigger, it emits a photon. People are using both of them. The first one, which I'm going to show, a parametric down conversion, is easy to generate, and it gives a very good quality of photon. But the other one, on-demand source, has been a bit difficult, harder to generate and build entangled state, but they are a bit difficult to use till now. But people are working on it so that you will have more efficient single photon source. So this is what the schematic of the way energy going up, when it's coming down, you get 2 photons. And these rings I'm showing here, I can't show it in the experimental setup because they have to be observed in dark light. The moment you are in dark and have CCD camera, you will not be visible. So I'm showing it here in the slides. But the setups which generates these photons, because these are long exposure thought, at any given time, there will be only 2 photons which is coming out. The moment it passes into crystal, it interacts, it comes in a conical shape. 1 photon will be here, other will be with the diametrically opposite. If 1 is here, other will be in another shape. So the moment I know a photon is here, I know a photon is at this point. But if you're trying to, these 2 photons will have different polarization, as an example. If one is H, the other one will be V. But now if you see there's an overlap region here, at the overlap region, we don't know whether the photon is from the ring from the top or ring from the bottom. So now I'm in the overlap region, if I'm detecting a photon, it will be H, but in the other one, definitely it will be V. So if this is V, the other one will definitely be H. Now that is what we call as generating an entangled photon, and that's there in the setup. And these are all the images which we have got from the lab here. I will take them all to to show. So I will show something here. So let's move to the experimental setup. So if you see here, so this is the laser source which we are using to generate single photon. The light is passing through this path. The laser is passing through here, and these are just an optics to make sure that it's entering. This is an optical fiber. From optical fiber, we are just bringing it to a setup where a single photons or entangled photons are generated. So you may not be able to see light here because they are at a frequency which is not visible. 405 is fine. It's a 405 input laser. It's passing through here, and there are some optics. We want sending some particular polarization. It's HV. So these are waveplates which changes the polarization, and then it passes through this part. This is a beam splitter where what it does is that this laser passes through, take one path, and here there's a beam splitter. So this is a very specific configuration which we have built in our lab to make 405 laser passing through, taking these two paths, and they pass through a crystal. This is a crystal where the single photons get generated. So it means that the 405 light which is passing through interacts with this crystal, and 1 in a million gets down converted, which means that they become 810 photons because the energy has to be conserved. I'm saying the double of wavelength, which means energy is going down. So 2 photons of lower energy are generated. Now those 2 photons also have to come out, right? So what happens is one is coming out like this, and the other one is coming out like this. So now these are the 2 points where the 2 pair, or like what you call a pair of photons, are coming. Now, whenever there is a photon which is coming on this to this input, there's another photon which is coming to this input. Now, these are our resource to do computation. So what we have done is that now these photons are entering into a small module, which we call as a 3-qubit module. There is one photon here, which is coming to this. There's another photon which enters to this module. But these 2 photons are chosen so that they are entangled. So we, while it is passing in itself, we make sure that there are entangled photon which is entering. And now this photon 1 which is going through gets, it takes a superposition of 2 paths. There's a small beam splitter. And what happens is that the moment it enters here, it takes both these paths simultaneously. And these are waveplates which can rotate them and then change the polarization of the photon. So which means that I've split and I can change the polarization of the photon in both the path the way I want. So now the splitting, or what we call a superposition, right? It's not, the photon doesn't split explicitly, but the superposition which it takes is a 1 qubit because of the path, which path is there, and the wavelength polarization change is another qubit. Now it again passes through, there's one again, right? So there's multiple beam splitters here. It takes multiple paths, and then I can have totally 4 outputs which are coming, and each would have a polarization path. So this kind of makes a 3-qubit system for us. There's another photon here that also makes a 3 qubits, but these 2 are entangled. Because they're entangled, so then that becomes a completely a 6-qubit system. So, but this, are we doing all the gate operations here? Yes, some gate operations. All the gate operations on the polarization degree of freedom are done by changing the waveplate. But if I have to have a photon which has taken superposition path, then to do gate operations, we send them to what they have just kept one of the interferometers here. Few are there. When the photon enters, photon in superposition enters 2 different paths. So there is an interferometer which has been built here to make them interfere, and that will be gate operations on the path degree of freedom. So the way we, as I said in the beginning, I was trying to say that when we have 2 photons, and if I want to make gate operations between those 2 photons, the gate operations are very difficult because they don't interact with each other. So what we are doing here is I'm taking a single photon, and then I'm taking both path, which path it's going to take, and the polarization as my qubits. So now I have 2 qubits here. Depending on the polarization, I can change the path, and on each path, I can change the polarization. So which means that I can do a controlled operation between the 2 different degrees of freedom and make a deterministic gate operation. So here I have a 3-qubit, but the four paths for the photon and the polarization can be controlled independently, and I can also have a controlled operations on the other qubit depending on state. And the gate operations on the path degree can be done using interferometers, and the gate operations on the polarization degree can be done by wave plates. In fact, we are using a plug kind of devices, right? These are the wave plates where I can plug them like a Lego blocks. I can change the wave plates. So we made it a modular one. Of course, alignments are a bit difficult, but we have designed a module such that it becomes a bit easier to align them. The polarizations have to be controlled, but we do have a polarization controllers to look at it. This is a simple, 6-qubit setup. We could generate a complete 6-qubit of maximally entangled state, what we call a GHZ state. So now after the light goes through all of this path, it will end up going to a detectors here. We have set of detectors depending on what polarization comes, which detector gets detected will kind of help us to map the output and then say what is the state I have measured. Right? So now this is a slightly an elaborated setup for a 6-qubit system. So we also did a simple 4-qubit setup and a 2-qubit also. So 2-qubit, what is the use of 2-qubit? These are like small devices, many of them could ask. So people talk about 50 qubits or 100 qubits or thousands of qubits to have a logical one. But one thing which is very unique to quantum systems is that, this I said, the duality, wave, particle and wave nature, or the collapse of wave packet is something which is a nature's given gift. So if I have to look for some security devices, then qubits are very, very useful. Like, for example, you all are familiar with OTPs, Q codes, right? We all get our OTPs, QR codes. These are all generated from random numbers. Where are these random numbers coming from? So they are coming from some computer program. So there is a program which generates bits. So now those bits, zeros and ones, are the one which people are using it for generating your codes, whatever is needed. But if I'm using qubits, then I can have it in superposition. Only when I'm making a measurement, it collapses. So what we did was to take a 2-qubit system, simple, like for example, we had this source we generated, and now that source, instead of having a 6-qubit, we have a very smaller module we generated a 2-qubit, and now that 2-qubit will create my 0001, 1011, like 4 possible state. And the moment you're measuring, it collapses to one of them, and that gives a random number. So I don't have any control on it. All that I need to do is generate a single photon source, put it into a 2-qubit system, and get an output. And that gets converted into an OTP. And this is a device here, which actually is kind of giving us shows setup where the whole 2-qubit source, whatever you see here, has been made compact, and that has been put inside. There is a source which generates, and there's a 2-qubit unit, and there is a detector. Everything is sitting inside this box, and now that will give us the system. I have you can see OTPs here. So you can create OTPs, you can create QR code, all of them, and this is running, and you can actually make them move around. We have made it. We have taken it to different cities, and it's also been currently used by a few agencies who need such kind of codes. So compared to other systems, when we talk about, like for example, you have, so there's a live binary which is coming, and I can get an OTP. I can get a QR code here, which is getting generated. These are like live devices, right? So if I'm looking at atomic system or a superconducting systems, which does need a cryogenic setup or a very bulkier setup, where 2 or 3 qubit might not be of very relevant, but with the photonic devices, it's much more, even a smaller number of systems can actually be moved around. Smaller number of qubit system can be moved around for some practical applications. So that's something which makes photons very unique compared to and other hardware. Got it. So I think I would see this more detailed description. So we do have some plans of how we want to scale up for a very large number of qubits, at least like, few tens of qubits in our lab in coming months to years. Once we have it, then whole of the scheme will be translated into a photonic integrated circuit where we can put them into a chip form and use it for computation. So there are challenges, but they are like, when we talk to students, sometimes students are the one who come up with the brightest ideas to address those challenges. So we look forward to have bright students working on it, working on these problems to address the challenges in real time and take it forward. Okay, so I would think I have add some slides, which more slides to take it. But, let's see. So all of this work which we have also are available in public domain for students who are interested. There are research papers, mathematical framework of how we are building qubits and how it has been put into experimental setups. Everything is published and it's an open resource. So in fact, when we say we have built 6 qubit, there is also results we need to show. These are just to say how we are moving photons in the paths in the slides you see. So this is even compared to some of the devices, 2-qubit devices, which people have built from other part of the world. Ours is reasonably a compact version. If you see, there's a Cambridge Quantum Computing, and then what you see here, which is working now here, gives a higher number of bits, because the way we did qubits, instead of just taking a single photon and have 1 qubit, we made 2 qubits to generate QR codes. So that increased our rate to a very large number. And to convince any colleagues who work in the same field here that these are get operations done very efficiently, we need to make many measurements. And we have done them all to establish, these are all the results to show how these are, if you see the lines there, the 2 paths, and when you showed the experiments, there's a photon takes some particular paths. So all those things are mapping up to the setup here, 2, 3 qubits. You could see this image and what we have, a 3-qubit module. And the way, if you look at this animation, I think it works, I guess. The video, you can see how the light is going, and it's going in superposition state, and it gets detected, and that's what is happening in an experimental setup. So similarly, we do have we did quite a few experiments to make sure that we have a good control of 2, 3, 4 qubit systems. So okay. So I think there's some slides were not visible in between, said, but it's all fine. I mean, the literatures are available. You can just look into our web pages and you get all the mathematical details of it and the experimental results. So how we build the 2, 4, and 6 qubit systems and the kind of tests. So this was the device we're talking about. What you see here and what is there in the slide. Comparison with the Cambridge Quantum Computing's photonic device, and then ours, which gives higher number, because instead of just taking single photon, we have 2 qubit, and these are the results which I'm talking about. Right? So yeah, so this is just trying to. Okay, so this is showing how the 3 qubit modules work, and how we implemented few gates, because when you see just controlling polarizations and the interferometers, we have implemented quite a few gates and use those keys to encrypt, decrypt images. So it means that 4-qubit device has some cybersecurity applications, and we could show. So what you are seeing here and what you are seeing in the slide and what I showed in the lab here, what you are seeing here as a 6-qubit setup is what is the correlation. The gate operations are shown there to have a 6-qubit entangled state implemented. So yeah, this is the final animation. It shows that how photon goes in superposition, because 2 photons are entangled, and then each one are again further entangled. It makes a complete 6-qubit system. Right? So in fact, we could even do a teleportation using a photonic computer itself. Like, I have a 3-qubit system, then I can prepare a state here, and then I can make the state reappear in some other place. Using the same setup, we had 2 different positions, and we could teleport at a quantum state by implementing gate. And that's also was something which we recently demonstrated in our lab. So with 2-qubit, 3-qubit, 4-qubit, and 6-qubit, we have some of the other experiment which we have demonstrated to say how we have some working modules. And all these details are available in public domain for anybody to explore and learn and understand. As a national quantum mission, we are part of, we are a consortium of other institutes, the SETS, CDAC, and JP Institute, where we are trying to scale up, address more problems, and we'll have more students who would like to join us and help us with more interesting problems which can be done in these systems. Okay, so thank you very much, and I hope this lecture was informative, and the lab, we would get to see something at the scale where everything is run in room temperature. We are not going to anything cryogenic in this setup. So over to moderators.
Hello.
Hello. Yeah, I can hear you.
Yes. So thank you so much, Professor Chandrasekhar, for this wonderful lecture. It was very informative, and we'll have some Q&A from audiences. So let me go through one by one.
Yeah, sure.
Yeah. So the first question we have is it reliable and robust using photons? How to ensure that it isn't degraded?
So, no, okay. So there is when we talk about photons, we already characterize our lasers. For example, when we say, I'm using a laser here, there is a coherence length for them. And we know that up to this length, the photons would not lose its coherence. And then every optical components which comes in between also adds some kind of disturbances, contributes for the decoherence behavior. So it had to be characterized. And how we ensure is that by doing measurements at the end, we do tomography, what we call reconstruction of density matrix, and that tells us how much it has lost from what it is. So using that, we put our reference point. So this is the number of gate operations we can do, or this is the length which photon can travel without being decoherent, and all the operations has to be done within this. So these analyses are already done for each system. So they are robust in that sense, because we can characterize them and we can. It's the same with all other hardwares, right? Even if superconducting qubit, they know coherence time, and so between that time they have to do gate operations, or else they're going to have losses. So in that sense, it's under control.
So we have one more question from Charan Tadipalli. What are the conceptual and practical differences between polarization encoded qubits in photonic systems and other photonic qubit encodings or other types of qubits?
So what are the difference or the characteristics? Sorry, what was the first?
Okay, I'll repeat the question.
Yeah.
What are the conceptual and practical differences between polarization encoded qubits in photonic systems? And
I got it. So I think conceptually they're all same. The moment I go and write a math for polarization or orbital angular momentum or a part degree, whatever I'm going to take, mathematical description should be same. Practically, what is the difference? Is that, so when I'm talking about polarization, I only deal, if there's a single photon, it's the H or V polarization I need to control. So practically, there is a different way of handling. And that's what is also uniqueness, or the difference in our system to compare to other one. Like when I say I have a 6-qubit in our lab, when we say that, what we mean is that 2 qubits in that are polarization qubits. Other 4 qubits are path degree of freedom for us. So now this is 2 different degrees of freedom acting as qubit. So practically, mathematically, they're all the same. Practically, for me, how I do gate operations on the polarization qubits and how I do gate operations on the part degree of qubits are different. So that's something which we have to take into account when we are trying to build. And that's how many of them do, whether you are dealing with polarization qubits or other. what components I would need. So when I was also showing the result for interferometer here, if I have to do an Hadamard operation on a polarization degree of freedom, all that I would need is have some waveplate like this, keep it in between on the path of the photon, rotate the angle into particular angle, then I would get an Hadamard operation. But if I have to do an Hadamard operation on the path degree of freedom, I need to send single photon in superposition. I need to make them interfere here. And that's when it becomes an Hadamard operation. So that's the difference between this is with this. Similarly, in a polarization or probably time bin, also another degree of freedom which people talk, where you have photons going in two different times, then you need to do operations between them. So you need to practically define operations differently for them.
Yeah.
Okay.
There is one question that we have, that is, so what's the better for scalability of qubits? IBM are using semiconductors, some are using atomic ones, like basically like neutral atoms and other and photons. So which is better to scale? In other words, I think.
Okay, so I think this is a question which nobody has an explicit answer. I know nobody can say that. That's one of the reasons why every nation or every researcher are encouraged to work on all the hardwares, because there are difficult questions to be addressed in all hardwares. So building qubits, superconducting qubits, superconducting circuits might look easier with an engineering efficiency. People have demonstrated for hundreds of them already. But the problem with them, when people started looking at scalability, is that the noise which is affecting, and then how you make a multi-qubits interact with them. And this is not just an engineering problem. This is also a scientific problem, because superconducting qubits are macroscopic items, right? So they also have some kind of noise, associated with its microwave environment, and they interfere, and the qubits don't remain clean for long. So, there, though you could have a very clean, smaller number of qubit system, scalability may be challenged unless somebody comes with an answer for that large scalability. So people are hopeful. There is no reason why you can't have. In a similar way, with the photonics, when I said there is an interactions issue, if you solve it, scalability is a lot more easier. But now there still needs to be some answers from the research communities to make them robust. So, unlike ion traps, they have better coherence than any other systems today, particularly compared to superconducting or anything. But then building ion trap qubit systems, scalable version, has been very hard, both scientifically and as an engineering task. So there are challenges with every hardware. So for next few years, I think all of them has to be seriously pursued until you finally find which one has. So might be a new candidate might come in. Then all the knowledge which you have learned from all of these things will be applied there, and will be efficiently be able to adopt to that and look at it. Does that mean that people who worked on superconducting or people who worked on photonics and all have to go back without any need for it? No. As I said, every science, every smaller device would have different applications. For example, this small 2-qubit system which we have here is still like an irrespective of, you can have a computer with some other hardware, but the smaller number of qubits photonic systems will be useful for secured quantum communications, which and other applications will be there. So there will always be some useful applications of all the qubits which you are looking at some scale, even if one of them succeeds to be the most efficient one for scalable quantum processor.
Yeah. So we'll take last two questions, sir. So one is like, why not we use any charged particles instead of photons?
Okay, so again, when people are talking about people can use charged particle, but the problem is the magnetic field affects them significantly, right? So any external radiations can affect them, and the noise destroys them. So that's one of the strong reasons you don't use charge. Like if I was using electrons instead of photon here, there could be, there is some electrical current supplies, many things which are using, they all have their own magnetic fields, and that would completely destroy the spin I want to control. And that's probably the strong reason not to use charge. But that doesn't mean that people are not exploring those options. People still who have some exploratory in that direction.
And the last question, sir, we are taking is, sir, we have learned that photonic qubits need accurate temperatures to hold on them. How do you manage these conditions here?
No, okay, it's not accurate temperature. It's not at all. You need to maintain some particular temperature. No, I don't know what was the motivation or what prompted them to look at accurate temperature. We have to just fix a temperature for the down conversion, right? Or the down conversion, I need to fix as that the two photons which are coming out should be of same wavelengths. So if the temperature varies, the two photons, not two in this instance, when I have multiple photons generated, all the photons should have a same wavelength, only then I can make them interfere. So if the temperatures in which the crystals are kept vary, then the wavelengths might be different. So I need to match wavelengths efficiently. And that is done by using temperature controllers, right? We have temperature controllers. There's an oven here and there's a temperature controller. I have to control the temperatures, which defines my outputs, photons, wavelengths efficiently. So we are working at room temperature, so it doesn't matter. Like as I said, this 2-qubit device is moved from Delhi to some other different places. There are different temperatures. They all work. It's just the wavelength changes depending on the temperature by a very small fraction. Not by like a large deviation. It will be a very small deviation.
Yeah. So sorry, sir, we'll take one more last two questions.
Yeah, please.
There is one question we got. To generate 3-qubit, we need 1 photon, but we need 8 paths. This makes space complexity. Why is that something? Yeah.
Yes, that is true. Yeah. So exactly. So that's a very good and important question. So people have asked us, like, can you scale it up exactly just using 2 photons? Can I build 20, 40 qubits and all? I would say you can build, but that's not scalable, like space complexity would come in. Why our 3-qubit or a 6-qubit system is not hitting the space complexity is because 2 plus 2 and 2 to the power of 2 are both the same, right? My answers would be the same. I will still get 4. So what we are doing is that I'm taking 4 paths for 2 photons. And then the polarization degree. Now, polarization degree, anyway, you have to just, for measuring them, you don't have to have an additional path. You can rotate your waveplates and you can measure. So even if I had multiple photons, I would have need the same space. So in that way, it is not hitting the space complexity. But if I were to scale by adding more qubits in path degree, then the number of paths required would again go in terms of 2 to the power of n. That is not considered as a resourceful scalability. It might address every other problem. I mentioned about the criteria required for computing. So it might meet all the problem, but it won't meet the resourcefully scalable because all the idea of quantum computing is to resourcefully scale. To address this problem, the way we are trying to do is that bring in additional degrees of freedom and both of them, if they explode, is to also have more photons coming in. So there's only one source here now, which gives me 2 photons and I have 6 qubit. I need to have a synchronized multiple sources, then I would have more photons. Then I could have a probabilistic interactions between those modules, 6 qubit modules, and then I can have 12 qubit system, and then we can scale up to some extent. But there might be some probabilistic, there will be some probabilistic behavior, but it will still be better than the regular probabilistic photonic computation scheme.
Yeah. And sir, the last question I think for this session, why are single photon sources important in photonic quantum computing, and what challenges exist in creating them?
Okay, so if I have to have a qubit, when I said qubit, it means that I need to have superposition, the measurement has to collapse. If I have multi-photons, then the measurements don't collapse. Like, I can take a laser, right? I can create a superposition of polarization and I can measure. The moment I measure, I'll detect both the polar. And if I take it to a circular polarization and measure, I'll get both the polarization. So the laser light won't help you. Only if I have a single photon, then it has to collapse and I will only detect at one point. So that's why single photons are very important. What is the challenge? As I said, and in the slides also I was trying to mention, generating single photons has not been easy. I showed a setup here, but people have taken decades to master the crystals so that you generate down converted single photons. The other method which people are trying to do is quantum dots and NV-centers material. There are also people who are using NV-center methods where they are coming up with ways to efficiently generate single photons. So that is a challenge. How do I efficiently and deterministically generate single photons? Here, we don't know when it gets down converted, but since two photons come, when I have one, I know definitely other one is there, then I can use it for computation. So that's the reason. I mean, the reason for having down conversion is currently they are the very efficient way to generate single photons, and single photons are very important to have the quantum characteristics captured. But people, I had also mentioned there are other degrees of freedom, right? Like for example, orbital angular moment or squeeze state, where they can still use qubits to look at it. But measurement is a bit difficult in them because you need to have a clear distinction in the shape to measure them and look at it.
Yeah. Thank you, sir. Thank you so much for joining this session and giving us a wonderful
you.
lecture. Yeah. So we'll try to all the audience. We'll try to post this material on LinkedIn, and we'll continue this journey with next sessions on Qkrishi channel. Thank you.
So thank you very much. So.